In this video, our goal is to find a basis for alt kv. So let's recall alt kv is the collection of all k forms on V, and k forms are just alternating k tensors on V. And to recall further, zero forms are just real numbers, and one forms can be identified with the dual space V star. So the goal is now to find a basis for alt kv. But before we do that, as a warm-up, let me just introduce one concept which will not really be used momentarily, but it will be needed in a bit. So this is the notion of the pullback of a form. Pullback of a form. And this will be very similar to what you would have studied. Given a linear map T from V to W, there is a pullback map which is often called T star from W star to V star. An analogous map we are going to define for K forms. Let T from V to W be a linear map where V and W are finite dimensional real vector spaces. As I have remarked before, if I don't mention what V or W are, you should take it as a finite dimensional real vector space. We will be throughout considering only finite dimensional real vector spaces in this section of the course. Okay, so we are given a linear map. If omega is a k form on W, then we define the form, T star omega of V1 to Vk by definition to be just omega acting on TV1 ... TVk. So the definition is exactly like how you define the dual map. If you have a linear map from a vector space V to a vector space W, then you automatically have a dual map from W star to V star. This is exactly defined in this way, and I want you to check that under the identification V star with alt 1V, the pullback that we have defined now agrees with the usual dual map you have seen in linear algebra. That this is a K form is left as an exercise, that this T star omega is a K form is easy to see and left to you. So let me describe one property of this pullback operation which we will repeatedly use, and I'm going to leave it as an exercise because it's very straightforward. Lemma, this is the chain rule. What it says is the following: let U, V, W be finite dimensional vector spaces, which I'm just shortening to FDVS. Of course, real vector spaces, I'm not mentioning that. So let F from U to V and G from V to W be linear maps. Let omega be an element of alt k W. Then G composed with F star of omega is nothing but F star G star omega. So pullback under composition behaves well, except there is a switch that happens. Happens for obvious reasons, because pullback goes from the codomain to the domain. Because of that, there is a switch. Now um, when you pull back the if you pull back a form under the identity map from a vector space to itself, nothing happens. When you pull back a composition, you get this reverse chain rule sort of. In fancy language, one can say that the pullback is a contravariant functor. I am not going to elaborate more, but if you are familiar with basic category theory, this is just saying in fancy language the same thing that we have stated in a pedestrian language. You can state in fancy language that pulling back of forms is a contravariant functor. Okay, now let's come to the actual part of this video. This was just to warm up. This is not going to be needed in what follows. We are going to get a basis for alt kv. Now, of course, we already know basis for alt 1v. This is just going to be e1 star, e2 star, en star, where e1 to en is an ordered basis of v. So this is just the standard dual basis that you are familiar with. You start with any basis for the vector space v, you automatically get a dual basis consisting of dual basis vectors. Now the idea is to somehow concord a basis for alt kv using these dual basis vectors e1 star to en star. Let's see how that goes. So we are going back to multi-index notation. Let I equal to I1 to Ik, where 1 less than or equal to I s is less than or equal to n, where n is nothing but the dimension of v. Okay, so you start with a multi-index, but not necessarily of distinct entries or anything. There could be repetitions, but it is sort of in an increasing, non-decreasing order. In any case, we define ei to be ei1 comma ei2 comma eik. So you just choose those basis vectors in this ordered basis corresponding to the indices determined by the multi-index. Okay, and here is the key definition. We also define ai to be just omega evaluated on this k tuple. After all, what is omega? So let me say fix omega in alt kv. So what is omega after all? It eats up a k tuple of vectors and spits out a number. That's what it is at the end of the day. I am fixing a particular k tuple, this k tuple ei1 to eik, then feeding it to omega, I will get a real number. That real number I am calling it ai. Okay, note that all of this is happening under a fixed ordered basis of v. Okay, now omega is not just any old function that eats up k tuples and produces for you numbers. It is multilinear and alternating. So think for a while and convince yourself that if I knew all the possible AIs as I vary all the multi-indices, I actually know the entire omega. I can determine omega by knowing these values ai by using multilinearity and the alternating property. In fact, because of the alternating property, if there is some repetition in the index, this ai is going to be anyway 0. So what will happen is, in fact, to determine omega in its entirety, I just need to know ai on some special multi-indices. I need to know only when I1 to Ik are distinct and increasing. If I know the values of ai on those special multi-indices, then I can determine the value of omega entirely on any vector by using multilinearity as well as alternating property. So that motivates the next definition and will sort of be the crux of the proof of or rather the construction of a basis. Definition, this is the definition of an increasing multi-index. Increasing multi-index. A multi-index I equal to I1 to Ik is said to be increasing if 1 is less than or equal to I1, less than I2, less than ... less than Ik. Okay. We denote the collection of all increasing multi-indices of length k with each entry less than or equal to n by this fancy script I superscript n k. Okay, so we denote the collection of all k length multi-indices, each entry being less than or equal to n by this I n k. Okay, now I'm going to leave an exercise which is just an exercise in pure thought. There is nothing much to do. Show that if I and j are two multi-indices of length k, that is two elements of I and k, then ei star of ej is going to be 1 if and only if I equal to j, otherwise 0. So what is this ei star I am talking about? That is exactly like the dual ei star where I was just an index and not a multi-index. We are going to define ei star and it's going to be very similar to the definition of dxi that we saw a bit before. So let me just give the definition of ei star so that you can solve this exercise. Let V be a n-dimensional finite real vector space. Let E1 to En be an ordered basis. For each I in I and k, I will be of the form I1 ... Ik. We define the k form ei star to be by definition determinant of EIR star acting on EIS, where R comma S run from 1 to k. Exactly similar to the definition that we already saw for dxi in the context of Rn. The same thing has been made a bit abstract, that this is a k form follows from the properties of the determinant. Of the determinant. Okay, now you are in a position to solve the previous exercise. Show that ei star of ej is 1 if and only if I equal to j and otherwise 0, exactly like how the dual basis vectors e small I star behave like. Okay, now we have set up everything, all the things are in place, the stars have aligned. We can finally construct the basis for alt kv. Theorem let I'm sick and tired of writing let V be a n-dimensional vector space. I'm just going to globally assume that from now the collection B, which is by definition ei star such that I comes from this I and k, is a basis for alt k v. So these special forms ei star form a basis. So consequently dimension of alt kv is n choose k, and that fact that it's n choose k is just basic combinatorics. Okay, the proof is not too hard because we have that exercise. So essentially I have shifted over the burden of proof to you. So proof first, let's see whether this is linearly independent or not. Suppose B is not linearly independent. Suppose this collection is not linearly independent. Then we can find a linear relation amongst the vectors. You sum up over all elements I in I and k. You get coefficients ai star is 0. Right? That's what a linear relation is. If the collection B is not linearly independent, you can find real numbers ai to make this equal to 0. But evaluating, so these sorts of proofs are all similar, but evaluating the above relation, not the relation, by evaluating the k form summation ai star on ej yields that ej is 0. Okay, hence this is linearly independent. Okay, now how do we know that this is going to be a spanning set for alt kv? Well, we do the usual tricks. Take an element omega in alt kv, define eta to be just summation over I and k omega of ei star. Okay, by definition omega and eta agree on the vectors, not the vectors actually, on the on ei. That's the correct way to say it, because ei is actually a k tuple of vectors, not just a vectors. So by the way I have constructed this eta, omega and eta agree on all the eis. Now by multilinearity and the fact that omega and eta are alternating, it is easy to see that omega equal to eta. Okay, so this requires a slight bit of thought. It is not profitable for me to write out this piece of thought. It's better that this piece of thought stays confined to your minds. So please think about this for a few minutes. You will get it that omega and eta have to be the same. So I have left a bunch of exercises related to this this proof in the notes. Please solve them. Okay, so if you are feeling utterly bored from what is going on, well, I can only sympathize with you. This part is a bit dry and boring, but After all, one has to cross the dry deserts to enjoy the tasty dates in the oasis. So the tasty dates are about to come. I'm going to prove a nice formula called the Cauchy Binet formula for determining the determinant of a product of two matrices when these two matrices are not square. Okay, so the setup is A is an n cross k, k cross n matrix, is a k cross n matrix, and B is an n cross k matrix. Question is, what is determinant of AB? Can you somehow find it in terms of A and B? Of course, you can't take the determinant of A and B because they are not square matrices. Surprisingly, this problem is related to the theory that we developed, especially this basis theorem that we just saw. Okay, so how are we going to go about doing this? Now, what we do is, once again, let me just think for a moment. Do I want this k cross n is a bit ugly. Let me just reverse the polarity or some thing. This is n cross k and this is k cross n. Okay. So, I mean, it makes no difference. It's just I want to end up with an n cross n matrix and not a k cross k matrix. Okay. Now, what we do is the following. Let I be in I and k, and I is just I1 to ik. We define AI to be the k cross k matrix, formed by the I1, I2 ikth rows of A. So A is an n cross k matrix, so it has n rows. You pick out the I1th, I2nd, ikth rows and shove it all into a matrix in the same order, and that matrix you just call it AI. Let's state the Cauchy Binet theorem. Cauchy Binet states the following. Let A be a k cross n matrix and B be a n cross k matrix. So contrary to what I said, I am going to end up with the k cross k matrix, but it's the same thing. N, k, I've just interchanged the roles. Then determinant of AB is nothing but summation I running through I and k. I reverse the script. I running through I and k, determinant of AI transpose, rather it's determinant of A transpose I. Remember, this I consists of k indices I1 to ik, and you are supposed to select the I1, I2, I3 ikth rows. So I must take the transpose first and then take I. So determinant of A transpose I, determinant of Bi. I can take Bi because B is already an n cross k matrix, so I don't need to take a transpose or anything. It's for this technical reason that I'm going to end up with a k cross k matrix. The way I have set up things, this will work out better, even though I would really like to end up with an n cross n matrix. Proof. So what we are going to do is, so before I do the proof, observe that if both A and B were both n cross n matrices, then just a moment's thought will convince you that this just gives the formula determinant of AB is determinant of A times determinant of B. So this Cauchy Binet formula is sort of an extension or generalization of the classical product formula for determinants. So we are going to introduce a bit of more notation. Denote the rows of A by A1 to AK. There are k rows because it's a k cross n matrix, and the columns of B by B superscript 1 to Bk. Because this is an n cross k matrix, there are k columns. Then the ijth entry of AB, the product is nothing but the dot product of AI and Bj. This is just this is just thinking about how the product of a matrix will look like in this notation for rows and columns. The ijth entry is nothing but multiplying the ith row with the jth column. In the standard way, you do A I K B K J, k running from 1 to n. That's what you typically do when you multiply, and that's exactly what I'm saying. This is just AI dot product Bj. Okay, now here is the clever part that makes this proof extremely elegant. I urge you to look at other proofs of the Cauchy Binet theorem and conclude for yourself that this proof is by far the most elegant. Fix the matrix A. Fix the matrix A. Remember, A was a k cross n matrix, and define for vectors x1 to xk in Rn. Define for vectors x1 to xk in Rn the map that takes the tuple of these vectors, or rather let me just put it in ordered pairs and put a power k here. Okay, so if you have an ordered k tuple of vectors in Rn, take it to determinant of Ax, where x is just this x1 in the first column, x2 in the second column, dot 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 xk in the last column. So this would be a n cross k matrix. So X is an n cross k matrix. I can multiply A with X. Then I take the product. When I take the product, I end up with a k cross k matrix, and I do determinant of that. Okay. So this is the function that is defined on Rn k. Now here is the extremely clever observation. This function is clearly a k form on Rn. Check. I'm going to leave it to you to check. Again, it follows from the basic properties of the determinant function. So call this form omega. The previous theorem tells us, that this omega is or omega acting at the vector b1 to bk is nothing but summation ai dxi b1 to bk. That's what the previous theorem says. If you go through the proof, that's exactly how we concluded that those ei stars form a basis. Ei stars in Rn are just nothing but dxi. Okay, where these coefficients are determined by the matrix A. Indeed, from the proof, we know that AI is nothing but omega of EI. Okay, which is nothing but determinant of AI. Think. Okay, so in the place of x, when you plug in EI, what happens, think about what happens, you will just conclude that omega of EI is nothing but determinant of course, there should be a transpose. This is nothing but determinant of A transpose I. Okay. But dxi of B1 to Bk is nothing but determinant of B. It's nothing but determinant of B. Okay. Determinant of Bi. Sorry about that. Dxi of B1 to Bk is nothing but determinant of Bi. So what we can conclude is that determinant of AB is nothing but summation I running through I and K, determinant of A transpose I, determinant of Bi. So the formula is proved. So this is an elegant application of the theory that we have developed. A lot of things have been left for you to check. They are all trivial checks that me doing it here is not really going to make you understand. Please grab a pencil and paper and work out all the details of this proof so that you have a clear understanding of what is going on. So we will develop the theory further in the coming videos. This is a course on real analysis and you have just watched the video on a basis for differential forms.